So, welcome back for our second lesson of algorithmic design. I hope everything was clear from the last lesson. However, I would like to recap some of the notion we introduced in the first lesson, so yesterday, just for be sure that everything is clear. So we saw the notion of calculability, we saw the notion of computability, and we understood that thanks to the Church-Turing thesis, we are able to say they are basically equivalent. Okay, and because of that, we decided to implements our algorithm in the RAM, which is a computational model quite easy to be handled. And we understood that we are not interested in estimating the computational time by looking at the execution time, but we are interested in asymptotic analysis of algorithms. So we want to avoid all the details in dealing with the constant time, execution time. And because of that, we introduced three useful notions, which was big O notation, big omega notation, and theta notation. And this is pretty much what we saw yesterday. So let's move on and let's try to introduce new notions which probably you already know from the very first part of the course, so advanced programming, but I still think it's useful to recap them. So let me move to the slides. Here we are. First of all, let's introduce some extremely useful abstract data type, the arrays. So the arrays are indexed homogeneous collections of values. By homogeneous, I mean that they are able to store exactly the same data type. Okay, so in any array you can always find this very same data type. So if the first element is a number, the second element should be a number, and so on and so forth. And they are fixed in length. So once you have defined them, but you cannot change their length. Or better, you can do it, but the price of rebuilding from the scratch a new array. Okay? So this is the first abstract data type that we need to know during this course. The second useful data type I want to recap is the single linked list. So a linked list is basically a sequence of values supporting the add and next operation. So given a single linked list, I can see the element in the first position. So in the example of the slides, you may ask whether what is the number in the head of the list, and you end up in discovering number -4. And once you are in the head, you can call the next operation and move from -4 to 0, and then to 1, and then so on and so forth. Okay? So this is again a quite different kind of data structure. In this kind, for instance, you are allowed to increase the size of the data structure itself simply by adding elements at the end of the list, or in the middle if you are able to support it by a proper operation. Third data structure, which is really important during our investigation about algorithms, is the double linked list. Okay, so what's a double linked list? A double linked list is a sequence of values, just like the single linked list, which however also support the previous operation. So from a certain element in the list I can move forward or backward depending on which operation I select. So by selecting a next operation I can move forward on the list, and by selecting a previous operation I can move backward on the list. Okay, so quite easy, nothing special. Again, also in this case you can add elements in the list itself, so by adding at the beginning, at the end, or in the middle, depending on which operation you are able to implement. Other two quite relevant abstract data type are the queue and the stacks. So a queue is basically a collection of value ruled by a FIFO policy. So what I mean by a FIFO policy, I mean first in, first out. This is basically what you do when you are trying to enter into a concert. So you wait for your turn in a list, basically in a queue. And or what you do when you try to buy some ham in your favorite market. Okay, this abstract data type support the add, so you can know the first element in the queue, support the operation of is empty, so you are able to test whether the queue itself is empty or not. It supports the insert back operation, so you are able to enlarge the queue by adding elements at the end of the queue itself exclusively, and you are able also to extract the first element of the queue. So the extraction is only possible at the end, and the insertion is only possible at the end of the queue. Okay, so exactly as I said, as in the case in which you are waiting for entering in a pub, or I don't know what kind of places you are used to. You are waiting for your turn, and once you are in front of the queue, you can enter. Okay. So what about stacks? So what are stacks? Stacks are again collection of values ruled according the LIFO policy. So last in, first out. You can imagine stacks like stacks of dishes. When you put many dishes one over each other, you end up with a stack. And of course, the best way to remove the stack is to take the element at the top of the stacks and not at the bottom. And this is a stack. So you can ask yourself which element is in the top of the stack. You can ask yourself whether, well, you can ask the stack to answer the question, are you empty? You can insert an element in the stack, so placing something on the top, and you can extract element by the stack, but only extracting elements from the top. Okay, so while in the queue you insert element in the back from the back, and you extract element from the head. In the case of stack, you are inserting element on the top, you are removing element from the top. Okay, so last element in is the first element to come out. Great. So these are all abstract data type. So I don't want to tell you how they are implemented. I'm simply telling you how they work from the functional point of view. Okay. And let's move on and let's see what are graphs. And first of all, I need to introduce them from a graph theoretical point of view. Okay, so I'm not talking about the abstract data type. I don't want to tell you how they are described and how we can deal them from the functional point of view. I simply want to describe them from a graph theoretical point of view. Okay. So from the graph theoretical point of view, a graph is a pair VE, where V is a set of nodes, and as you can see from the slide, You can imagine them just like dots, which are labeled by the name of the dots themselves, and edges, which basically connects pairs of nodes. Okay, well, let's move on. Okay, so there are two kind of graph. The first one is undirected graph. So in the slide you can see there's no direction in the edges. So E and A are basically belongs exactly in the same way. So I can move from E to A and can move from A to E exactly in the same way. And there are a different kind of graph, which is the directed graph, in which the edges as let's say an arrow are arrows. So you can move only exclusively from one of the two nodes to the other one. Okay, and in such a case, the node from which you are moving on, from which the edge is moving on, is called source, and the node reached by the edge is called destination. Okay. In such a case, also the set of nodes is basically a subset of the Cartesian product between V and V itself. Okay. So you can imagine E just like how can I say it? Just like sets of pairs. Okay. This is it. So other few important notions that we will investigate during the course will be path and cycles in graph, of course. What's path? A path is a sequence of contiguous edges moving from a certain node to another one. So in this case, for instance, there is a path from D to E, or vice versa, because we are dealing with an undirected graph. And as you can see, I can reach E from D simply crossing over these edges, which forms a path. Okay? So quite easy. And what's a cycle? Well, a cycle is basically a path in which the source and the destination of the path coincide, so are the same. Such in this case. So in this case we have a path, and we are moving from E to E or from A to A and so on and so forth. Okay? Great. So what's a connected path graph? Sorry. What's a connected graph? So a graph is connected whenever for each pair of nodes you are able to build up a path between them. Okay, so going back, let me go back here. For instance, in this case, on these slides, you can see a graph which is not connected because I'm not able to build a path between, for instance, E and F. So there's no path between E and F, and then this graph is not connected. Okay? Great. So what's an acyclic graph? So of course an acyclic graph is a graph which does not contain cycles. Okay? And what's a tree? A tree is a connected and acyclic undirected graph. Okay? So here you can see a tree. This is from a graph theoretical point of view. We will see that this notion, so the notion of tree, is slightly different from the computer science point of view. Okay. However, please remember, from a graph theoretical point of view, a tree is a connected, acyclic, undirected graph. Okay. So let's move to abstract data type point of view, so from the graph theoretical to the computational computer science point of view. A tree in a computer science is organized in hierarchical levels, okay? And to do so, we have to identify a specific node called root. So once you have a graph, a tree, as you can see in the slide, you need to pinpoint a node which is, how can I say, elevated at the rank of root of the tree. For instance, in this case, we may select A as the root of the graph. By doing this operation, you are basically, as you can see, organizing the tree into levels. Okay? So now you have the first level, which is built up by root, then the second level, which is made up by the nodes directly connected to the roots, and so on and so forth. But we will see it later on. So what's the depth of the node? Well, the depth of the node is the distance from the root. Okay, so in such case, in this case, for instance, we have B, the node P, and if we ask ourselves what's the depth of B, well, the depth of B is basically 1, because the distance from B to A is 1. What about E? Well, E is distant 2, because the shortest path from E to A has length 2. So the depth of E is 2. Okay? Quite clear. As I said before, we can, by using this notion of depth, we can identify levels. So what's the level? A level in the tree is basically the set of nodes having the same depth. So in this case, A is the level of depth 0, the set containing B and F is the level of depth 1, the set containing C, D, and E is the level having depth 2, and so on and so forth. What if we add a new node just below F? Well, that node will belong to the depth to the level C, D, E, and I don't know, G, for instance. Okay, so it's not really important that the nodes in the same level are connected to the same node. It's just important they share the same depth. Okay. And okay, so since we are dealing with a hierarchical data structure, we can identify, for instance, the parent of the node. So what's the parent of the node? Is the node connected to the node we are dealing with, which has depth -1. So for instance, in this case, we can see, we may wonder what's the parent of D. Well, the parent of D is B, because B is the only node connected to D whose depth is the node of depth of D, -1. Okay? Is the depth of D -1. Well, of course, there is just one node which has a parent, and this is it, the root. Okay? So the root hasn't any parent, of course, because it is hasn't any node which is connected to other node whose depth is smaller than the node of the root itself. Okay. Symmetrically, once we have identify the notion of parent of a node, we can also identify the notion of children of a node. So what's the children of the node? The children of the node are those nodes which are connected to the node we are dealing with. So in this case, for instance, we are dealing with B, are those nodes which are connected with B and whose depth is the depth of B +1. Okay? So in this case, for instance, the only nodes connected to B whose depth So distance from the root is the depth of B plus 1 are C, D, and E. Because, of course, the depth of A is 0, while the depth of B is 1. So A, for sure, is not a children of B. Please notice that these notions of parent, children, and so on and so forward can only be given because we have defined the root of the graph. Okay, and if the graph is seen as we saw from the theoretical point of view, we don't have in any hierarchy, and so parents and children have no sense. Okay. Great. I leave you as an exercise. Try to see what would be the tree if we had chosen F or B instead of A as a root. Okay. Speaking about children of the note, two notes are called siblings if they share the same parent. So, for instance, C, D, and E are siblings because they share the same parent, which is B. Okay? And by extension, of course, since we have parent, siblings, and so on and so forward, you can define the notion of aunt, you can define the notion of grandparent, and so on and so forward. Okay? So this is a matter of family, let's say. Okay? Let's move on the notion definable on graphs, and let me deal with leaves of a graph of the tree. Sorry. So what's a leaf of a tree? The leaf of a tree is the leaves of a tree are all those nodes which hasn't any children. Okay. So in the graph we are dealing with, we have C, D, E, and F, and they are all leaves. Okay, because they haven't any children. And while A and B, which on the opposite have children, are called internals node of the tree. Finally, well, not really finally, but almost finally, the height of the tree is basically the maximum depth among all the leaves of the tree itself. So the depth of this tree is 2 because the maximum depth among C, D, E, and F is 2. Please observe in this example that we also have a leaf which whose depth is not 2, is smaller than 2. In this case, for instance, F, whose depth is 1. Okay. Is it clear? Can you see me? I hope so. Can you write me something on the chat just to test whether is everything working or I'm talking to myself? We will see. Okay. So just to conclude this recap about some notion that you may probably already seen during the first part of the course. Okay, great. Thank you. During the first part of the course, we will see the notion of n-ary tree. So what's an n-ary tree? An n-ary tree is simply a tree in which the nodes have at most n children. Okay. So for instance, let's see the graph. Let's see the tree in the slide. The tree in the slide is a binary tree. So a two-ary tree, a binary tree, because the arity of the children, the maximum arity of the children for each node is 2. So each node has at most 2 children. Please notice that the node E, for instance, has just 1 children, okay? While of course the leaves have no children at all, okay? Great. And finally, and this is really the last notion I want to recap, the notion of complete tree. So what's a complete tree? A complete tree is a tree in which all the level but the last one have n children, okay? So we are dealing with an n-ary tree, so in this case a binary tree. All the levels but the last one, so the level which correspond to the height of the tree itself, so all the nodes in the level but the last one have exactly 2 children, okay? Okay, this is clear. And this is all I want to say about what we really need during the course. Let me just well, no, I don't want to make an example. Do you need some example of graphs just to be I couldn't say improve your knowledge about graphs, or are you fine with what we saw till now? This is exactly one of those cases I mentioned during the first lesson. I cannot see your face, so I don't know whether I can push forward on hold back and make more example on graphs. If you need more example, I can try to draw something. Otherwise I will move on. Well, in the meanwhile, let me see whether I can. Okay, I can move to the next slides. Okay, this is it, and this is it. It's clear enough. What a graph used for real life? Well, one of your colleagues are asking whether why are useful graphs, and well, the real question is what cannot be modeled by using graph. Okay, so for instance, just to make an easy example, some easy example, just think to Google Maps. Google Maps is a network of streets which are modeled by using a graph. Okay, and each city in well, this is a real tough course approximation, but just imagine a situation in which each city corresponds to a node and each street corresponds to an edge. Okay, this is a graph. Or for instance, we are dealing with the coronavirus, and let's imagine we want to map all the people which have all the movement of the people which have the coronavirus right now, just to find the patient 0. And this can be done by using a graph. So I know that, for instance, just to make an example, I have the coronavirus, I took from one of my colleagues, and my colleague took it from someone else. So really the notion of graph is fundamental in any possible domain if you want to model something in computer science. Okay, I think this is really one of the notion most useful notion in computer science. Okay, and we will see it during the course. Okay, so let's move on, and let me introduce let me just, can you see it? Yeah, the new topic we are going to deal with. So this is an unusual topic, so unusual in the sense that it is not usually introduced in a basic course on algorithmic design, on algorithm. However, I think that in some sense it is useful because it gives us an example of why algorithmic design can be also useful in really understanding a problem. Okay, so we will see it. But first of all, to see this problem, of course, we need to define it. Okay, so let me recap really briefly what we already saw, what we already know, which is the row-column multiplication between matrices. So just to be sure that we all know what we are talking about. So let's assume to have two different matrices, A and B, and you can see on the slide the dimension of the matrix. So by saying that matrix A is n times m, I mean that it has n rows and m columns, and B, the second matrix, has m rows and l columns. Okay, so if this is the case, we can define the multiplication between, please notice the number of column in A is exactly the number of rows in B. If this is the case, we can multiply A by A times B and obtaining a new matrix whose dimension is nl, so n rows and l columns. How? Simply doing the following things. So if we want to evaluate the element in position 1, 1 in A times B, we have to multiply the first element, in A by the first element, the first element in the first row of A by the first element in the first column of B. And this should be summed by the second element in the first row of A times the second element in the first column of B, and so on and so forward. So by summing up this multiplication, so this elements multiplication, elements white multiplication, we end up with a value which is the value of the first element in the first row and first column. So what about the element in the first row and second column? So this can be evaluated simply taking the first row of A and performing exactly what we did previously with the second column of B. And this operation goes on until we have the whole A times B. Okay, so this is simply what we did from the secondary school. Probably. Well, almost of you probably already saw this row column multiplication in the secondary school, and for sure you already saw it during the degree. Okay, the first degree. Okay, this is all I want to say about this type of multiplication. So now that we know what I mean by A times B, we can define the problem. So let's take two matrices A and B. Please notice that we are taking two square matrices, so the number of row and the number of column should be the same. Okay, and by taking these two matrices whose sizes are the same, we want to end up with their multiplication. Okay, so we're taking A and B square matrices n times n times n, and we want to end up with A times B. Okay, please notice this is just to easy the problem, so we don't want to deal with a non-square matrix just to simplify the problem itself. But of course, we can generalize the solution to non-square matrices. Okay. I think this is all. So a naive solution. Let's see a naive solution, an algorithm solving the problem in the naive way. So this is the naive solution for the matrix multiplication problem. So I'm taking A and B, and the third parameter, the first parameter C, would be used as output, let's say. Okay. I'm going through all the possible rows of A, all the possible columns of A. I am assigning 0 to a temporary value, and then for all the columns of A, I'm keeping going through the element, multiplying the elements of the ith rows of A times the element of the jth column of B. Okay. So this is basically what we do when we are asked to compute A times B. Let me see, because I moved. Okay. Sorry. Okay. So this is the naive solution. What's the complexity of this naive solution? Okay. Well, first of all, let me notice that the naive solution basically mimes the definition. Okay. We have 3 nested loops. So the loop in which we are going through the index I, the loop in which we are going through the index j, and the loops in which we are going the index k, and they are all these loops basically keep repeating all their operation from 1 until n. Okay, remember the number of rows and the number of columns of both A and B are the same, and they are n. Okay, so these 3 loops basically are indexes from 1 to n. The inner block, so the block in which we keep multiplying and summing up A to its previous values, takes time theta 1, of course. Okay, so the overall execution time is theta of n cube. Okay, it's quite easy to see. So the A plus A, big A, and so on and so forward, that takes time theta of 1, of course, because this is inserted into a for loop whose range goes from 1 to n. Of course, these for loops takes time theta of n. This is inserted inside another for loop, and so we have complexity theta of n square, and then we have another loop, and so we have theta of n at the power of 3. Okay, this is all. So the complexity of the naive solution is theta of n cube. Can we find a better algorithm? Well, to be honest, I was asked with precisely this question many years ago, and my answer was I don't think so. But of course we are dealing with this topic in the course, and guess what? Of course there is a better algorithm, which is quite weird because the naive solution mimes the row column multiplication definition. So we have an algorithm which is miming, is doing precisely what the definition specify as row column multiplication, and still this is not the best algorithm to performing this operation. This basically means that the definition, the row column multiplication definition, is overwhelming, gives us more information than needed, okay? Which is strange, because usually definition should be, how can I say, as reduced as possible, okay? So this is quite strange from my point of view, and that's why I insisted to introduce this part inside the code. So let's now that I spoiled the result, let me move on and see what strategy can be helpful in finding a better algorithm. So and let's see the divide and conquer strategy. So what about in splitting, to solve our problem, what about in splitting the two matrices A and B into blocks? Okay, so let's imagine to split A in 4 blocks, A11, A12, A21, A22. And let's imagine to do exactly the same for B. So B11, B12, B21, and B22. Okay? Now, by doing so, we are able to solve our problem by using this equation. Okay, so this solution, or also the solution, is split into blocks, as you can see here, and each of these blocks can be computed as this equation report. So, for instance, the block C11 can be computed as A11 multiply B11 plus, where this plus is element-wise plus between matrices, plus A12 multiplied by B21. Okay? This is enough to compute this block of the matrix, of the final matrix. Okay? So this is a strategy. It's just a way to see the things in different way. But this gives us the chance to build up a recursive algorithm. Okay? Why? Because what is contained into these two parentheses, of course, is again a multiplication between matrices of the same sizes. So these two multiplication can be performed again by splitting these two matrices, smaller matrices, so these two blocks, in other smaller blocks. Okay? And so on and so forward, until we end up with blocks having just one element of the original matrix. Okay? Now let's try to figure out the complexity of a possible divide and conquer strategy. Okay? So let's try to see what's the complexity of the algorithm, of the recursive algorithm used by using this strategy. So, as I said before, the plus is an element-wise matrix sum. So what I'm doing is basically summing the element in first row and first column of A, well, of a certain matrix A, plus the first element in first row and first column in B, and so on and so forward. So since the matrix I'm dealing with are matrices whose size is n times n, the complexity of performing this operation is of course theta of n squared. Okay? Now, in the previous, as already mentioned, in the previous equation, the time symbol it refers to the usual row column multiplication. So again, we can do it in time. Again, we can do it by applying the divide and conquer strategy. And as already noticed by splitting the original matrix into blocks, all the matrices A, J, K and B, J, K, which are basically blocks, have size n divided by 2 multiply n divided by 2. Okay? So, as said, we can define a recursive algorithm whose receipt, let's say, is the following one. So if the row of A is smaller than 2, so if the rows of A, if A contains exclusively one element, we can apply the Naïve multiplication algorithm. Okay? And otherwise, we can recursively compute the multiplication between the blocks. Okay? And they are 12. And then from the multiplication of the blocks, we can compute the sum between the blocks we mentioned before. So let me go back. We need, of course, multiply this by this. We need multiply this by this, and so on and so forward. And then we need to perform the sum between these two. So what I'm saying here is that we need to perform the sum and return. At the end, we can return the overall matrices. Okay, so once we have computed all the blocks belonging to C, which is the matrix multiplication between A and B, at the end we can return the result. Okay, this is just a sketch of the algorithm. I don't want to detail more than this, just to give you an intuition of what's going on here. Now, what's the complexity of performing this operation? Well, the complexity to perform this operation is, can be detailed in this way. We need 8 multiplication between blocks. Why 8 multiplication? Going back here, well, of course I need to multiply A1 by B1. I don't know, let me see. Okay, of course we need to multiply A1 by B1. We need to multiply A21 by B1 2. We need to multiply A1 by B1 2, and so on and so forward. So if you try to count all the possible combination, you end up in seeing that we need for sure 8 blocks multiplication. Okay, and again, if you count the number of sums, well, of course you have one sum for every block in the final matrix, so they are 4. So the complexity of the algorithm is the one we can see here. So trying to figure out the complexity of the algorithm is the one you see here. So if Tm is the complexity of the algorithm is equal to 8 times the complexity of the algorithm applied to the blocks, to smaller matrices, okay, plus 4 times theta of n square, which of course is equivalent to theta of n squares. Is it clear? Please notice that here I'm basically using theta of a function just like was a number, but actually is a set. But I think you can figure out what's going on here. So by writing this, by using this notation, I'm basically saying I want to take theta of 4 times n squared. Okay, this is, I mean, from a formal point of view, is not really correct, but you know what I'm talking about. At least I think so. Okay, and here we are stuck. We are stuck because here we have a recursive complexity equation in which to establish the complexity of evaluating m, we need to know the complexity of m on a smaller instance of the problem. Okay, so how to solve it? Okay, let me see here. Someone is asking me something about square parentheses between 1 and 2. I think he's talking about these two equations, these 2 points, and probably is correct. Let me see. Yeah. Here we need a comma between 1 and 2. Okay? I think this is the question. Okay. So how can we solve it? Let me move to something nicer. Okay. Here we are. So first of all let me rewrite our equation. So the previous equation. So we had something like wrong color. Tm of n is equal to, and here 8 times, and let me change color, and I will tell you why in a while. Tm n divided by 2, and let me change color again, plus theta of n squared. So why I changed color in writing this equation? Well, because I want to stress the fact that this is due to sum. So this is costs. This is the costs of sum. Okay. While this is the cost of recursive call. Okay, great. Now let's assume for a while, let me change again the color. So let us assume, well, let me write in this way, sorry. So let C n square be what? Be the function defined by theta of n squared. So be this one. Okay? So in the equation I wrote by using the theta notation the cost of the sum. While now I want to do in some sense a step back. I want to write in a proper functional way the cost of that sums. And so I use, since we are dealing with the theta n square functions, set of functions, I'm choosing one of them. They should be not distinguishable from the asymptotic point of view. So I choose the easiest one, and the easiest one is c multiply n squared. Okay. Now, once I've done this this operation, I can write what is called let me write here recursion tree. Recursion tree. So what's the recursion tree? The recursion tree is a way to compute the complexity of an algorithm by estimating by estimating the cost of each recursive call. Okay, so it is basically used when you have a recursion equation, a recursive cost equation, and so each level of the tree will describe the cost of a certain level in the recursion process. Okay, we will see. So the first at the very beginning we are performing the first call of our algorithm. The first call of our algorithm will cost from the sum point of view, so the sums of the first call of our algorithm will cost of course c time n square. Okay, I'm not telling you what's going on in the recursive steps. I'm just saying, let's assume to have solved the problem, the recursive problem. So now we need to perform the sums. So the last part of recursive equation, and the cost of the last part of recursive equation is c times n squared. Okay, and this is the root of our recursion tree. Now, of course, just before performing the sums, we need to perform the recursive steps. The recursive steps in our algorithm simply perform the multiplication of the blocks, if you remember. Okay, so I've split the two matrices in 4 blocks and I need to perform blocks multiplication. And so we know that this recursion, the number of recursion needed to solve our problem are 8, because we said that we need to compute 8 times the blocks multiplication process. So we can draw, and again let me change the color, we can draw ideally, I'm not going to do all of them, 8, so let me see, arrows, 1, 2, 3, 4, 5, 6, 7 and 8. Okay, and this, oh, this is really awful, let me redraw it. Here we are, and these arrows basically model the recursive steps. They are I haven't drawn all of them because of course I don't have many space for write them, but ideally we have 8 arrows modeling, representing the recursive steps of our algorithm. So basically the block times block multiplication. Okay, now we may wonder from the sum point of view, so from the last part of the equation point of view, what's the complexity of this recursive call? Well, of course, let me change again color. Their complexity will be c, because the c is preserved, times what? Now, the first call need to sum up object whose size is n squared. Okay. Now, after the first call, we need to sum up object whose size is half of the previous size. Okay? So, okay. The previous size, let me see. Okay, sorry. So, after the call, we are dealing with the object whose size is n-ary. And due to the equation, this would be multiplied by n, by themselves. So the complexity will be the complexity of the sums in the first depth of the recursion call would be n squared. And this will also hold for all the recursive steps. So for all the arrows moving from the first call, we will have this complexity, time complexity, again, exclusively for the sums. Okay? So, first call, recursive step, first recursive step, second recursive step, so on and so forward. Last recursive step will cost, in terms of sums, again, this. Okay? Quite easy. Now, this process will go on, of course, until we are dealing with a matrix whose size is 1 times 1. Let's try to figure out what's going on in a generic step. So in a generic step, and let's hope to have enough space. In a generic step, so let me draw things in this way, just to change my slides. And so here we are. So after a bunch of recursive call, we end up in a situation in which the complexity would be c times n divided by what? At each recursive step, I'm basically dividing by 2 the size of the matrix I'm dealing with. So the size of the matrix after I recursive call, so after a sequence of I recursive call, is of course 2 at the power of I. Okay, so this is the size. So n divided by 2 at the power of I. This is the size of the matrices I'm dealing with in my chain of recursive call after I recursive call. Okay, and of course this should be squared, because we at this point, at that level of the recursive call, we need to multiply matrices having size n divided by 2 at the power of I. And to sum up matrices of this size, we need to perform 2 divided by 2 at the power of I square number of operations. Okay, and this situation holds for all the level. So if you keep evaluating all the recursive call at this level, so after a sequence of I recursive call, you would end up with this situation. The cost of the sum at this level will be c at the power, n divided by 2 at the power of I at the power of 2. Okay, so for all the recursive call at this level, the cost of the sum will be this one. And as I said, for n, what's the 8 of this tree? Since at each step of at each level of this tree I'm divided by 2n, and since my recursion end up when the size of my matrix is 1, so the 8 of the tree, the 8 of this tree, going back, so the 8 of this tree, so let me write in this way, the 8 of this tree will be, guess what? Will be logarithmic. So the 8 of the tree is logarithmic base 2 with respect to n. Okay? So now we have built a recursion tree. We know which collect basically all the cost for the sums in all the process of computing the matrix multiplication A by B. And so now we can evaluate the overall cost of our algorithm simply by summing up all the elements in the tree. So all the nodes, all the values labeling the nodes in the tree. So let me go there. So what's the cost of the first call in terms of sums? The cost of the first nodes in terms of sum, of the first call in terms of sum, is of course Cn squared. So what's the cost in terms of sum of the second level? Well, the cost of the second level, since we have 8 recursive call, will be C multiplied by 8, where 8 is oh well, let me change the color just to stress the fact that we are dealing with a certain number of recursive call. So the cost of the second level would be 8 multiplied by C and 2. Okay, this will be the cost. So what's the cost? What will be the cost of the ith level? So this level, the cost of the ith level will be let me write this. So how many, well, the point is how many recursive call we have at this level. Well, since at each level we are basically multiplying by 8 the number of recursive call, the number of recursive call at this level will be 8 at the power of I. Okay, while the cost of each in terms of sum at each recursive call, for each recursive call in this level would be, of course, C and 2I squared. Okay, quite clear. Now let's try to sum up all these terms. So since this is a generic cost for the ith level, and since we know that the tree has a number of an 8 which is logarithmic in the number of in the size of the original matrices, we can deduce that the complexity of our algorithm is basically equivalent to the sum of all the terms I put on the right, which is this one. So for all I going from 0 up to log 2n, okay, I need to sum up 8i multiply C and divided by 2 at the power of I squared, which by the case is basically equal to, let me write equal in a better way, to I0 logarithmic base 2 of n. And now I'm simply applying some algebraic notion. So this would be C. Let me avoid to change the color right now, just because I want to focus on the algebraic part of this stuff. So this would be c multiplied 2 elevated to the power of 8 multiply n square. Okay? This is it. So this is the complexity of our algorithm, which let me again try to simplify it. So we just wrote something like Tm n equal to the sum for I 0 logarithmic base n of c multiplied to the power of a n square, which of course can be written as c at the power of c multiplied n at the power 2 plus the sum for I going from 0 to the logarithmic base 2 of n of 2 at the power of n of I, which of course is equal to c multiplied by n square multiplied by 2 at the power of logarithmic of 2n plus 1 minus 1. Okay, and again by simplifying it we end up with c n square multiplied by, so here I'm simply evaluating this sum which is basically 2 at the power of logarithmic base 2 of n plus 1 minus 1. Okay, this is a Gauss equation theorem, sorry, and so let me simplify it. So this is basically again 2 at the 2 multiply so now 2 at the power of logarithmic base 2 of n is of course n, and this 2 is due to this plus 1 minus 1. So the complexity of our divide and conquer algorithm is this one. Okay? Yeah. Okay, so guess what? If we try to simplify it, we end up with c multiplied n cube minus c n cube n square, which of course belongs to theta of n cube. Okay, so the complexity, the overall complexity of our divide and conquer strategy is theta of n cube, which by the way is exactly the complexity, let me go back to the slides, exactly the complexity of Strassen. Let me see. Okay. Is exactly the complexity of the Naïve algorithm. So this strategy doesn't help, actually. So you may wonder, so we waste a lot of time in computing everything, and at the end nothing is going on. Nothing went on. So this is just what we already saw. You can find it on the slides, don't worry. And probably I also provide you the PDF of what you saw during the presentation. However, the point is that the divide and conquer approach had too many recursive calls, and so its complexity is basically just like the naive algorithm. We waste a lot of time in doing things that is not helpful from the asymptotic point of view. Okay, but someone, and in particular Professor Strassen, asked himself, can we rephrase somehow the problem in the divide and conquer strategy in a way to avoid some of the recursive calls? Okay, is it possible in some sense to avoid at least one of the matrix of the blocks multiplication in the recursive call? Okay, yes, it is possible. And now I will show you how Professor Strassen was able to reduce the complexity of the naive algorithm and of the divide and conquer algorithm. Okay, so he was basically a mathematician, and so he performed a lot of testing, and he discovered that by doing all this operation, it is possible to avoid one blocks multiplication in the recursive call. Okay, and this is enough. We will see this is enough to reduce the complexity of the overall algorithm. Okay, so now I don't want to go through all the possible steps, but and motivate them. I don't want to prove the correctness of the algorithm, because I mean it's just a bunch of computation. It's not really interesting from the algorithmic point of view. What is interesting from the algorithmic point of view is the idea that we are able to reduce the complexity of the definition, let's say, of the matrix multiplication. So Strassen basically start by building up 10 different matrices by using exclusively sum and subtraction between matrices. Okay, well, better, between blocks. And these are the definition of the 10 different matrices built up in this way. Once you have these 10 different matrices, you can evaluate 7 different matrices by exclusively applying multiplications. So you will have, instead of having, just like in the divide and conquer algorithm, 8 recursive call, you will have 7 recursive call. Okay, which doesn't seem very interesting. 7, 8 is just a matter of one, but actually is really relevant from the algorithm point of view, and we will see in a while why. Okay. And once you have built up these 7 matrices in this way, again, I don't want to go through why in this way you will be able to compute the matrix multiplication between A and B. However, once you have built up that matrices, you can again use sum and subtraction to build up the blocks of the matrix multiplication between A and B. And here you can see, again, for sure we have to perform a larger number of sum between blocks with respect to the divide and conquer strategy. Here we need to perform 10 sums. Here we need to perform 4, 6 and 8 sums, but from the algorithmic point of view, so from the asymptotic point of view, the cost of this step and the cost of this step is r theta of n squared. Okay, so despite the fact we are performing more sums, the complexity from the asymptotic point of view of these sums doesn't change. Okay, And what about the recursive call? Well, again, the recursive call has, of course, a recursive equation that we are going to see in a while. But instead of having 8 matrix submatrix multiplication, just like in the divide and conquer algorithm, we have 7 matrix multiplication. Okay, submatrix multiplication. Let's see the complexity. So as done for the divide and conquer algorithm, we have a complexity equation which should be resolved to get the complexity of the Strassen algorithm. But let me stress the fact that here we have a 7. So in this point of the equation, we have a 7 instead of an 8. So if you go back and look at the slides, let me do it just for the sake of here. Okay, so this is the complexity. This was the complexity of the divide and conquer strategy, and basically the complexity of the Strassen algorithm is the same, with a small difference, which is this number. So in the divide and conquer algorithm we have an 8. In the Strassen algorithm we have a 7. Okay. Now let's try to compute the complexity of the Strassen algorithm, so the algorithm proposed by Strassen. And to do it, again, we may use the recursion tree. Let me avoid to do it on the whiteboard, and let's see what's going on simply by looking at the slides. Here we have an error. Sorry, I just noticed that the leaf are labeled by 1, and they should be labeled by C. But I mean, I will solve the problem for the next lesson. And if we try to compute the complexity by level, as we did for the divide and conquer algorithm, we notice that now the complexity is this one. So you can see it in the last part of the slides. Of course, the slides contains all the computation. I don't want to go through all the calculus. I mean, you can do it by your own. And however, we discovered that the complexity is now rather different with respect to the divide and conquer strategy, because now the complexity is theta of n at the power of logarithm base 2 of 7. Okay, which is rather similar to the previous one, because the previous one was n cube, which is basically theta of n elevated at the power of logarithmic base 2 of 8, not 7, but really makes the difference. As a matter of fact, if we try to plot the two complexity as I did in this equation, in this slide, sorry, you may see how the blue line, which is the divide, conquer, and the Naïve algorithm complexity, is rather steeper than the complexity of the Strassen algorithm. So the Strassen algorithm is not quadratic. Is again not quadratic, more than quadratic. However, we still have a really important increase in performance in terms of asymptotic complexity, with matrixing having not that much, not really that incredible sizes. Okay, so taking a matrix having say 600 rows and columns still already made a difference. So dealing with matrices having these sizes still already show you the differences in applying the Strassen algorithm with respect to applying the Naïve algorithm or the divide conquer algorithm. Okay. I think that more or less this is all about the Strassen algorithm. I hope you enjoy it because it's really surprising. It's really surprising that by analyzing the problem you end up in a solution which is, let's say, smarter than the definition itself of the problem. Okay, and moreover, this algorithm gave me the chance to show you how to evaluate the complexity of a recursive algorithm, because we saw the recursive tree technique to evaluate the complexity of the algorithm. So this is all. If you have any question about this topic, I will be they will be welcome, and I will be happy to answer to them. Otherwise, I think we will have a lesson on Tuesday, and we will try to implement the Strassen algorithm and see the difference between the rather easy, let's say, sketch of the algorithm we saw before in the part of the divide and conquer strategy, and the implementation of the algorithm, which is not really that easy, and in some sense a little bit tricky. Okay, are you still there? I hope so. Okay, thank you for the attention, and let me know if you want to change something in the course, and again, any suggestion will be appreciated, and any question will be hopefully answered into the next lesson. Bye.